Good, now we can hear you. Well, good to see you again. And Ian is going to be telling us about monolithic micro LED arrays using organic thin film transistors. So, Ian, would you like to share your screen?
Sure. Let me go to that, share, and then got a thing. How's that?
That's it. Good. Now,
Okay.
if you go to full screen mode,
Yep. Going to go to full screen mode.
yep, and then hide that little thing at the bottom,
Hide
and
that little thing at the bottom.
you're good to go.
Excellent. Right. I'm going to put my timer on. So, thanks everybody. Welcome from dark and dingy London. It's a very cold, damp, dark night tonight. So I'm Ian Jenks. I'm from SmartChem. I'm going to talk today very briefly about some of the things that SmartChem does, and then I'm going to introduce you to a new and exciting development that we're announcing with monolithic micro LED displays. So I'll go as fast as I can. So we make inks. We make a stack of inks that allow us to a stack of organic inks that are based on organic semiconductors, and that allows us to make a range of transistors. Sometimes we sell our materials as single layers. Sometimes we mix them up and pattern them and produce transistors. And sometimes we make big arrays of those transistors and make displays. I won't go into how we actually make up our inks, but suffice it to say, we make a full stack of materials that can be placed on a substrate. We make a base layer, organic semiconductors, gate insulator, sputter-resistant layers, and passivation layers. What's unique about what we do is we do this at this solution process, but we do it at 80 degrees centigrade. And that means that we can do it on low-cost glass and plastic, and it's a photo curing process, which means that we can pattern them using direct laser writing. And they've been designed, even though they're organic materials, to be able to be processed on amorphous silicon lines. But of course, we don't need the high energy consumption machines, the PECVD machines. And you can look at the know-how at a different time. So how do we actually take our things to the market? Well, our strategy is very simple. We enable customers to make the impossible, whether that is because they can't afford to build new infrastructure and they're looking for a low cost, whether that is because they want to do something on a different type of substrate, or as I'll show you in a minute, whether it's simply to do something that they cannot do any other way. I apologize for the ambulance. And our strategy is we show them what our materials can do, in particular the low temperature processing, but also our ability to maintain mobility as we go to very short channel lengths. And I'll show you a little bit about that in just a moment. We've developed a set of EDA tools that is an add-on module to the Cadence's EDA tool system, and we help them design products using our module with on the Cadence platform. And then we have a foundry service that allows us to make products prototyping at our foundry in the north of England, and to transfer that to their own process lines. We've just heard a lot about micro LEDs, and very elegantly put in much more detail than I could ever give. The reasons for going to LEDs are absolutely overwhelming. Much more efficient light source, self-emissive. they can be hugely bright and well above the need to well above the brightnesses that you need in order to be able to see them in daylight. They are use a lot less power. They last a long time, and you can read them in daylight. So there's and within the boundaries and the puts and the takes between OLEDs and micro LEDs, and micro LEDs with color conversion with quantum dots. What I find really exciting about the market today is that it's open for change, and it hasn't really been open for change. If you think about the number of different technologies that have come to the market in the last 30 or 40 years, it's very few. And now we have a very exciting time where lots of people are trying new things. So uh, let's think about micro LEDs and the way they're actually made into displays today. So you take your red, green, and blue LED wafers, you singulate the chips, and then we've had a lot of very interesting talks about the problems that people are trying to solve as you take those chips and you mass transfer, everything from pick and place at the big signage down to um, all sorts of sticky pads and mass transfer, and you put them over onto a pre-existing backplane, and then you either solder them or you um, or you laser weld them. It's a process that people are struggling to get to yield efficiently, and are having to develop new technologies for pick and place to pick and place and do repair. So not so many months ago, I asked the team, as the CEO, you're allowed to ask stupid questions, aren't you? So I said to the team, well, why don't people just take these wafers and actually process transistors on top of them and completely eliminate the need for any sort of pick and place? And the answer came back, well, that's kind of difficult thing to do with amorphous silicon doesn't quite have enough power in any case. They're all high temperature processes. And if you do that, then some of the metallization that you've placed onto the LEDs actually leaches into the quantum wells and destroys them. So I said, well, guys, we've got a low temperature process. Why can't we do it? And just eliminate all these transfer losses. So what you see on at least my right-hand side of the screen is actually our very first wafer, where we've taken a 4-inch gallium nitride patterned micro LED wafer, and we've solution processed directly on top of that an organic thin film transistor array to drive a variety of different pixel pitches and tags. And so I guess the burning question is, did it work? And first, we believe that an OTFT has actually been directly patterned on top of an LED wafer, and and this particular pattern is actually a pattern that is designed to sit behind an LCD as uh, a mini LED backlight. Um, our initial tests show on that particular set of wafers that we have backlight brightnesses of over 100,000 nits, and I'll show you in a minute the roadmap to over 500,000 nits. We're currently in the process of scaling it up to higher resolutions. We believe that we can pattern up to 2,500 ppi with some modifications to our lithography tooling. Currently, we pattern down at around 2 microns, and we're now working to be able to pattern sub-micron. And then you can use it either as a quantum dot sheet to color convert it into the white, or you can actually either print or photo pattern quantum dots on top of that in order to be able to produce a full color display. So customer specific things that we're working on at the moment. So V2 is the one that you saw. I shan't tell you what happened to V1, but version 3 is actually our high brightness designs, which are in processing at the moment. The mostly designed to be backlights for LCDs, and to be actually an intimate contact with the back of the LCD, with brightnesses up to 500,000 nits. And then version 4, and I'll show you the first bits that are coming off that, which we're working on with UC Santa Barbara. Steve Denbars is on our board of directors, and we work closely with Suji Nakamura. For those who don't know, Suji won the Nobel Prize for inventing the blue LED, and those are specifically aimed at generating higher PPI devices. So looking then, and the first result is a 55 pitch, 48 by 48 display.
Ian,
And
just a
you can
heads up
see
that
that
you
it,
have just a heads up that you have 5 minutes left.
yep, absolutely. I'm actually just coming to the end, so we've got a bit of time for questions. So, and please don't tell me there's not enough contrast to that. I haven't even popped the sapphire wafer off the back of it yet. So again, a monolithic approach to making small scale displays, principally aimed at augmented reality and virtual reality. We're now in the process of moving to 300 millimeter wafers, because the next question people are going to ask is, what about costs? I believe that there is a roadmap to being able to produce VR size VR size displays for in the low tens of dollars. We're looking at whether people. So we have a process for popping the wafer off the back of, actually then popping the whole of the sapphire substrate off the back of the LEDs. We're looking at ways of dicing them up, and then we are integrating more electronics. One of the properties that we're able to do is do pseudo CMOS using our OTFT transistors to develop gate on arrays, and moving down to submicron processing. So that's smart, and what we're doing in micro LEDs arrays, eliminating the need for any sort of mass transfer process. Thank you.
Thank you so much for the excellent presentation. Do we have some questions for you? I think the first question is, the question is, maybe you can stop the screen share so you can also join me on the stage just with your camera. The question is, seems as though there is some disagreement as to the level of circuit driver complexity that is required in active matrix pixel arrays for micro LED displays. Can simpler driver architectures, such as these, achieve the promise given by micro LEDs?
So I think they can. One of the great, so when you start to look at the ways that people are driving micro LEDs today, and some of the, where people are putting them on, IXO and LTPS, and even on CMOS, you end up actually, high mobilities are not your friend. You have to artificially lower the mobilities by changing the W over L, because otherwise when you get down to low luminance levels, the threshold is simply too steep to be able to cope with the very small fluctuations in voltage that you get in those systems. And hey, you need a bit of luck, and I'm delighted to say that the balance of our mobility and our slope, but also our ability to have very stable operation on both positive bias stress and negative bias stress. Those are two issues that we have managed to solve within our core chemistry. Means that we don't have to compensate for in the same way that other designs do for being able to drive very stable current in changing environments. And then we are able actually to add, gate on arrays, mux demux circuitry using our NMOS.
Sounds good. Ian, maybe I missed this, but how do you deposit the actual OTFDs on, monolithically?
Well, so we take the wafer, we put a planarization layer over the top of the LEDs. We then solution coat, so a mixture of spin coating, photoresist, wet etch, and metallize the top, and then we drop the vias down and metallize it. So um, it's not two separate bits. We take the wafer and we simply solution coat the transistors directly on top of the wafer. And then we're actually in a position where we can remove the sapphire substrate from the bottom. And so actually the passivation layer you can either put it on a plastic sheet if you want to stick it to something, or it's simply that's it, and you can and put it directly on the. You can have sufficiently high resolution that you can put it directly on the back of an LCD display, or you can put quantum dots on the front and make a high resolution display in its own right.
That was very interesting. And you mentioned threshold voltage stability. So how
Yep.
stable are these? And the reason I ask is because often you might have to drive these micro LEDs with a high current, and that usually for OTFDs doesn't it's not good news.
Well, um, so our uniformity. Well, two answers to the question. One is our uniformity over of mobility and threshold current over a wafer is within 5%, and we drive relatively large transistors that are relatively stable. Um, so typically unencapsulated in atmosphere. Um, then we have shifts in the threshold voltage of between 1 and 2% at 60 degrees, 60 degrees. Um, 60 degrees, 60% humidity, driving them at voltage swings of up to 50 volts. So very, they're pretty rock solid. It's just an
Yeah.
inherent property of our OTFTs, which are fundamentally different in their core chemistry to anybody else's.
Yeah, I mean, well done to you guys. I think you guys are solving a lot of the key challenges of OTFDs. Going with a full stack of materials, making it compatible with photolithography and laser patterning, so it can
Yeah.
fit into existing fab lines, and really demonstrating applications where, as you said, the market is still more open. There's no settled design, and so the chances of adoption are higher. So yeah, thanks a lot for your presentation and for joining us. It's
My
always a pleasure
pleasure.
having you.
And anyone who wants me, they can find me through you guys. Thank you.
Yeah, and also, I mean, if you could hang around for the meet the speaker after the last session, some people might
Yes,
want
so I'm not sure if I'm going to be able to do, but Selena will be on there, and she'll make sure that